let's try to make it into an SIW structure. Okay. The best. So, what is the idea? So, the idea is, the simple idea is, I don't know whether I have talked about this earlier. We can take any microstrip line. So, the idea can be the idea of SIW, which is given by KU. So, that can be reached by two ways. That can be reached by two ways. First is, we can think we have a microstrip line. Okay, three ways we can think. Three ways. We can think of a microstrip line. We can think of a like two-way transmission line. This I think I have earlier also talked to you about.
Yes,
So
sir.
two-way transmission line. We can think of a microstrip line, and another we can start to think of a rectangular metallic waveguide, KR waveguide.
Hmm.
In the two-way transmission line, if we connect both sides with lambda by 4 short-circuited lines, this side and this side, like this, and keep on joining them together but with length of, let's say, lambda by 10. In between, the distance between these two short circuits should be less than lambda by 10, so that it looks like a seamless connection. And this way you can connect and connect, and it will look like a, this will directly emulate like a metallic waveguide, right? You can think
Right.
of it
Yes.
like this. Yeah, metallic waveguide. And this is how you can think. And because of lambda by 4, this short circuit, due to quarter wave transformation at this point, can look like a open circuit, and your energy will fundamentally go through this line, and there will be a signal line and this return line. Okay.
Hmm.
So this
Yes, sir.
can be emulated in this structure also. You can think from this point the main signal is current is going like this, and the current is coming back from this, and we have connected short circuited extra section lambda by 4 section on both sides. Now because of this lambda by 4 sections on both sides, it is giving you a lambda by 2 total dimension. This broad waveguide dimension becomes lambda by 2. Now, when we are talking about lambda and lambda by 2, all these are actually different. So, in case of waveguide, this lambda is not lambda 0, not lambda 0, but your guided
Hmm.
wavelength, which is a resultant wavelength because of the how the wave actually propagates with inside the waveguide. Because it bounces back and forth, and so there is a lambda guide, lambda g, which is
Hmm.
higher than the lambda. Okay, which is higher
Yes, sir.
than the
Hmm.
normal lambda. So this is the lambda g of your waveguide. Now let us go back to, so one of the major problems of waveguide is that this dimension is directly dependent on lambda. So at lower frequencies, what will happen, because c equals to f into lambda, or lambda equals to c by f, right? Lambda is equal to c by
Hmm.
f. What will happen at lower frequencies, your lambda will be too big, so your waveguides are big. So we can have,
Hmm.
I don't know, if we want to have, we can search waveguide size comparison, and maybe I don't know, we can have an image, I don't know, uh, side by side waveguides should be there, not there, but you can see here, you can have a list. See W at 20. So at higher frequency, at 26 gigahertz, your waveguide dimensions are 18 mm by 8 mm. Whereas at higher frequencies, we go,
Hmm.
your waveguide dimensions are much smaller. So at lower frequency, as S band or something like that, your waveguide size will be very big.
Hmm. Yes.
Your S band waveguide size will be very, very big. You can kind of get an idea about the structure. So these are quite big structures. Okay. Versus S band
Hmm.
waveguide versus, I don't know, versus, like, if we can find something X band waveguide, should be somebody should have made a comparison. I don't see him. The idea you are getting, I guess, the waveguide dimensions will be much different actually. Nobody has done a side by side comparison. That's odd. That should have been. Anyway, we can find it out somewhere. But the idea is that here is here you can have some idea. See, you can have some idea. WR90, WR60. You can see. Look at the dimensions a little bit. They are bigger, smaller. You can see, but it is not the perfect one. S-band and C-band. Yeah. See the waveguide dimensions how they can vary. Okay, smaller and higher. That is how much they can vary. Okay, so that being a problem, this is a good one. This picture is a good one. This can directly show you because of the waveguide dimension difference, the frequency difference. Your waveguide has, as you go for higher frequencies, your waveguide dimension becomes smaller. Okay, that's you can see. Now, but still at lower frequencies, say at C band, 5 gigahertz or something like that, your dimension will be quite big. Okay, so how to tackle that? So one of the primary ideas was to fill this internal structure instead of air. If we fill it with some kind of dielectric, because what happens when we put it in some kind of dielectric, because its permittivity is higher, your electric field will be highly concentrated on in the so if so for a say for a air waveguide, your electric field is having a zone like this, with a dielectric field waveguide, it can happen that is like this. So most of your energy is concentrated here. So for the same frequency, your most of the energy will be contained in this A dimension. So if I feel it for the same frequency, we can reduce the dimension of the waveguide, or in the same waveguide, we can go for even lower frequency. That's the idea. But there is also some other things. We cannot arbitrarily set any waveguide frequencies. You can see if you go for again any waveguide dimensions, you can go to our website, everything RF, everything RF, waveguide sizes or waveguide dimensions. I can see that each and every waveguide has a cutoff frequency and a cutoff frequency of the next mode. And you can see, so basically, see, this is 0.32 gigahertz is your recommended frequency, and your cutoff frequency is 0.257. So you can calculate it 0.257 into 0.32, sorry, 0.257 by 0.257 by 0.32, what happens? So 80%. So normally it is this 80% rule. Okay. So on the other hand, it is like 0.257, no, sorry, 0.32 by 0.257. Yeah, 0.32 by 0.257. So it is 25% higher. You can see. So and it is always says that you can go for WR, 90 also, which is X band. Let us see whether this rule is followed. 6.557 into 1.25, 8.19. See, 6.5%, 8.2 to start with. That is the idea. And one more thing is, so the cutoff frequency, whatever the cutoff frequency is, 25% higher.
Hello?
That is the recommended started frequency. Getting my point?
Yes, sir.
Hello.
মাঝখানে internet disconnect হয়ে গেছিল। Hello,
Oh,
sir.
okay. And right now you are getting.
Yes, sir. Yes.
So 6.557 is the cutoff frequency of the waveguide. That we are getting from this dimension, lambda by 2 dimension. And from this 6.557, with 25% 25% higher, we start our recommended operating zone. And I shall show you also why we are doing this. So in our waveguide last week's waveguide design, yeah. So at 6.557, 6.557, we have the cutoff frequency where our impedance is very high. Impedance is very high. That's why no signal is going through. So and this is the cutoff frequency. And you see 25% higher, 8.2 gigahertz. That is where your this exponential, this slope of the impedance actually tapers down, and then it becomes a little bit linear.
Yes, sir.
And this is the reason why we are utilizing it here, not utilizing it here. You can see the rate of growth here, or the this what do you call tan theta of this one is much higher than this section. If you can think of it as a piecewise linear section, is much higher this section. So this is, there is a huge variation of impedance from 6.557 gigahertz to 8.2 gigahertz, and after
Yes.
that it settles down a little bit. So after, in this zone, you can think of, say, from 850 ohm it is going to 450, so 1 by, so half. But once it is at 8.2, which is the recommended zone for this 433 ohm, to your end of this zone, that is 314 ohm, now it is that ratio is much less actually. So that is much more useful. So 433 by 315. So this is something, yeah, 1.37. Instead of earlier it was 2 times. In this zone there is a half reduction, 50% reduction. In this zone only a 37% change is there. Okay.
Yes.
So this is the reason why. Another thing is, if you think about the last day, did we plot some modes?
Yes,
So
sir.
yeah, so we had plotted your surface current, yeah,
Vector
but
J,
if
sir.
we,
Yes,
yeah,
sir.
but if we also plot not only surface current, why should we plot? So if we also plot our E field, magnitude E field, say, yeah, sweep 7 gigahertz, I don't know, yeah, 10 gigahertz, there is the center. So here you can see what is happening. So this is the mode basically. You can see the mode. The mode is, here you can imagine a minima 0 at this point. Then there's a
Yes, sir.
maxima. Then there is a 0. Okay. So and this way also there is a 0. Then there is this maxima. Then there is another 0. Maxima
Maximum
or
and
minima,
then.
whatever. So this is the mode, you can say. So, and this mode is the T10 mode. If we look at the field input field mode, yeah, you can see this is the T10 mode. At the center you have the highest values, and at the it tapers down. So if we do plot the amplitude values, it will look like a sinusoid, like this way. Okay,
Yes, sir.
getting my point, na? Okay. So this
Yes,
is
sir.
that level. But this is okay for 8 to 12 gigahertz. What will happen at 12 gigahertz? Let us also plot that. So at 12 gigahertz, what will happen? So this is the mode for, I shall not do it here. So this is the mode for 10 gigahertz. But at 12 gigahertz, what will happen? Look at the where it is becoming blue at the both sides. So it is becoming blue almost this. If we look at the top view, at almost this point and this point. Okay. What will happen at 12 gigahertz? So we can again select the structure and plot fields and E and magnitude E, but this time let us go for 12 gigahertz, which is the highest end. Till 12 gigahertz it is useful, remember, but still you will see what is the problem going to be. So at 12 gigahertz, you can see that actually it looks like quite elongated, right? This mode is now looking like quite elongated, because you can see that at
Yes, sir.
uh, at 12 gigahertz at 12 gigahertz, we only need this dimension. From this point to this dimension is enough for a mode. So this way also we are having too much a mode. So what is happening at higher frequencies? There is a chance of two modes getting there. So there is a chance of two modes getting there. So at lower frequency, what is happening? We can have one mode, like this,
Yes,
one
sir.
mode. At higher frequency, there is a, if we so for the same waveguide, the mode will look like only this. So what is the direct effect? It is becoming elongated, looks like this. Okay, but in actuality there is a chance that this will happen. So this is the T20 mode. So if we plot it like this, it is the electric field is like this. Here the electric field is this. So 0, maxima, 0. So there is a virtual short circuit here. And then there is again a maxima, and this becomes T20. Okay.
Yes,
So
sir.
this is
Yes, sir.
the different, completely different mode. So we try to avoid oversized waveguides, and that is why you see in every there is this higher at a higher cutoff frequency, because there is a T20 mode. So we avoid going to T20 mode. We use from T10 mode, and this is the starting of the T20. We avoid to use that, but we can take precautions and still use it for higher frequency. It is not, because waveguide looks like a high pass filter. You can see the result for last day. It is actually working. Even at 16, 18 gigahertz, it is working. But there is a but we have to take precaution that higher order mode does not get created, or even if it, so that your energy is concentrated in single mode. Otherwise, you will not be able to use that energy will not wasted if we are not able to
Yes, sir.
tap into that energy. Yeah. So that is the idea. Next, what we can do. So okay, now going back to our original discussion. So going back to our original discussion, we have now understood that if we feel dielectric, then your waveguide dimensions can be brought down. Your TE10 mode can be concentrated in a very smaller A dimension. And this has, people have been doing this also. People have been doing dielectric field waveguides also. Dielectric field waveguides also. Well, there are these kind of structures where you fill it with a dielectric. But this KU came up with the idea that what if we create that in a PCB itself? So what if that, again, from this original idea, we can think of small microstrip lines and take a via and connect it to the bottom and make this length lambda by 4 and keep on connecting them. Keep on connecting them, and the distance between each of these extra sections, extra lines, the distance in between is lambda by 10. And that way it will be a seamless array of this kind of structures with short circuit at lambda by 4 division. And now this can be thought of as a similarly you can transform it into a waveguide kind of structure. So if we connect the whole top with metal only instead of a single microstrip line, if we connect the whole thing, and at the right these sides we create vias and connect the top to bottom and both sides and this side also, then now we have again successfully created a dielectric field waveguide only, where the side pins are actually replaced, side wall is actually replaced by this array of plated through holes or vias. Plated through holes or vias. So that is the idea how SIW came down. Now why did you, so the dielectric field waveguide was already solving the problem, but the thing is then you have to fabricate a metallic box and then you have to fill it with a the substrate. Here we are already utilizing the low cost PCB making processes and just converting it into a SIW structure or waveguide structure, and that is how it becomes substrate integrated waveguide. Okay, so that being said, once this idea is set, then we can think of this same structure that we used earlier that day, this air waveguide. Let us just think of it instead of air field waveguide. So we had made it air, right? So instead of making it air, what if we make it into a substrate? That way it will be a substrate field waveguide. Okay, so let us do that.
Yes, sir.
Let us just change the properties of this substrate into not from air to some other website, say alumina. Okay, alumina. Let us do it at alumina. And alumina and not alumina. Alumina will be too well. Let us go for Teflon. Let us go for Teflon. Okay. Teflon has a rigidity permittivity of 2. Why Teflon? Because it is actually easier to calculate. Let us go for Teflon. And yeah, now it is Teflon. And let us do the same simulation. And if our idea is correct, our cutoff frequency will shift much lower. every dimension is same, right?
Hmm.
Every
Yes, sir.
dimension is same. So if we go for our sweep, and we know it was earlier was 6.557. So let us, I don't know, let us try for say 3 gigahertz, and let us see it if it goes to 18 CZ. It does not matter. So let us do that, and yeah, let us analyze this. And if our discussion is correct, then what we should see that our cutoff frequency has shifted much lower, because our now the
Hmm.
same waveguide can be used for a lower frequency. Okay,
Hmm. Yes, sir.
our simulation has started. Let us wait a little. I think that is this is the idea. So once this is done, this will be a dielectric field waveguide. So why am I
Yes, sir.
saying
Hmm.
this way? So my main idea is to instill in you an concept that our SIW structure is nothing but a dielectric field waveguide. So
Hmm.
whenever we are trying to simulating SIW structure, we need not simulate an SIW structure. We need not put an MPTH and everything. We can design it as a dielectric field waveguide, and later on we can replace the side PEC layers with PTHs. That way it will be SIW.
Hmm.
What is the beauty of that? Because that simulation will take much less time. See, my simulation is already completed. So we shall go through the
Yes, sir.
whole
Hmm.
idea that I just told you. So yeah, you see, it has gone much less.
Hmm.
So let's quick record this reported parameter and see our ADX marker. Our cutoff frequency has now shifted to 4.55 gigahertz. Now let us do
Yes,
some
sir.
quick
Hmm.
calculation to give you an idea why it shifted. So our this thing, how do we get to scientific? I think here it is, right. Yeah. So where let us. So we have already seen the Teflon dielectric constant is 2.1. So let
2.1.
us do.
Yes. Hmm.
Let us do the square root of that. That is 1.449. My earlier cutoff frequency was 6.557. Let us say 6.6
Hmm.
by 1.45 or something like that, right? 1.45 and 4.55 gigahertz, and this is 4.55 gigahertz. See,
4.5. Hmm.
were you able to connect?
Yes, sir. Hmm.
So basically, when you use the substrate integrated waveguide or dielectric field waveguide, what we basically did, we so earlier there was a lambda g. This lambda g was the effect of a wave, whatever I said, the wavelength bouncing back and forth over the walls. Further, it will be
The
we can think of
formula
it
was
as
cutoff
the
frequency divided by the
yeah.
root
So
under the
the
previous
new
extent.
wavelength will be
Hmm.
lambda g by root over of the epsilon r that we are fitting.
Epsilon. Hmm. Yes,
And
sir.
this
Okay.
is nothing new. This concept is relatable to your this concept. So in microstrip line, your lambda g was lambda 0
Hmm.
by root over of epsilon r.
Epsilon. Hmm.
Okay, it was
Yes, sir.
lambda 0. Okay, like if lambda 0 is your normal wavelength.
Hmm. Normal
Only
level.
thing
Hmm.
in waveguide is that now that lambda 0 will be replaced by lambda g, which is the guided wavelength of the waveguide, that
Hmm.
thereby over epsilon. So
Yes,
everything
sir.
that we
Hmm.
calculate for a waveguide thing, every dimension, every that can be directly by 1 by root over epsilon r, and that is my
Epsilon. Hmm.
dielectric waveguide dimension and my SRW dimension. Okay.
Yes, sir. Hmm.
Okay. Next, we shall do another experiment. So now our design has shifted. So to make it the same waveguide, how do we make it the same waveguide? To make it the same waveguide, what we need to do is again we need to follow that 25% rule that my operating frequency should start at 1.25 times of the cutoff frequency. So actually, in this one we can use it. So again, whether that is correct, let us see here. Again, this is at 4 point. You can see the very sharp slope, and then it settles down around here, right? It settles down
Yes,
around
sir.
here, and let us again do that calculation. 1.25 times. So this is 4.57, 4.55.
Right.
So yeah, 4.55. So 4.55 into 1.25. And yeah, 5.68. Let us look at 5.68. Yeah, somewhere around there. We can again see it is settling down. Okay. So
Yes,
this
sir.
is the idea. This is the idea. Another thing that I would like to bring to your notice is look at the impedance here. 223 ohm.
200.
Earlier, the impedance was 339 ohm or something like that.
Yes, sir.
340, 300, more than that, 300, 350, 400 ohm. Now the impedance has also come down because of your epsilon r. The impedance has also come down. We can think of this. Why is this coming down? We can think of this. Let us go to my slide, and I shall also put my thought into that. Why my impedance is coming down? Because this concept of impedance in waveguide is a slightly different from microstrip, but it is very important to understand. So my first study help, I don't know. I think I have it in study help. Yeah, yeah. So in this impedance equation, you
Yes,
can
sir.
see there is B by A. Your B by A dimension.
Dimensions.
And if we keep the same, and then there is root over mu by epsilon, right? And
Yes,
now
sir.
my epsilon has changed. So,
Dielectric.
because now epsilon has changed to so earlier it was 1, now it was, so basically this was
2.1.
for air waveguide. For air waveguide, this
Yes, sir.
section root over mu by epsilon would be root over mu naught by epsilon naught, which is 377 ohm.
Epsilon.
Yeah.
Yes,
But
yes, sir.
in this case, now our bottom epsilon r is 1.45 times lesser than the impedance earlier. Okay. Now we can also do
Yes, sir.
that. We can also try to see whether it is conforming to same idea, that it is also scaled by 1.45 times. So earlier you remember our impedance was around 350 something like that. So 350 by 1.45, 241. See, so
Yes,
our
sir.
impedance is directly scaled. As well, just like our cutoff frequency is scaled, our impedance is also being directly scaled.
Skilled. Yes, sir.
And that's a beautiful thing. That's a beautiful thing. So basically, we can bring down the impedance also by putting the electrics inside
Yes, sir.
in the same waveguide dimension. Right? Now, in the same
Yes, sir.
dimension, what we shall do now, we shall actually try to make the same 8 to 12 gigahertz W190 waveguide and try to see how much changes are. So the idea, if our idea is correct, we should our this A dimension should be 1.45 times less than our earlier.
Yes, sir.
Yeah, so 22.86 by 1.45. Okay. And it becomes 15.76. So 15.76. Okay. We shall not do this here. We shall put it into a optimetrics. So add parametric, add A dimension, starts 28.6. Okay. 22.86. And my A dimension should be 15.76.
15.4, I think.
15.76.
76, 76, sorry.
15.76, and let us do this in three values. Let us have a three value. I just want to see that it is seamlessly going down. Okay, one thing
Yes,
will
sir.
happen, and let me warn you. Our B dimension should also be scaled.
Yes, sir.
Not only our A dimension, B dimension should always also be scaled, because if we want to keep if my A dimension is going down, there are two things here.
B dimension
In
is
our
also.
impedance equation, you have a B by A. So keeping the same impedance, if you want to keep the same impedance, our B and A should be reduced by the same
Scaling
factor.
factor should
Point
be
one.
same. Yes.
Yeah. Second is, if my B dimension is too big, B dimension is too big, then it will start looking as if it is a square waveguide, and that brings another problem. So
Yes, sir.
earlier my B dimension was like this. Now we are bringing it down, say like this. Now it looks like a more of a square
Yes, sir.
waveguide. As we bring it down,
Square wave.
and in square waveguide, again there is a mode problem, because the energy can be distributed like this, or it can also be distributed like this. And whenever there is something can happen, it will happen. Although in a controlled simulation, this can be seen perfectly, but actually in actual structure, your another mode will be created. Okay, so
Yes, sir.
again energy will be lost. If actually this square waveguide is actually used, where when we are using ortho mode transducer. So I have planned a work for you with ortho mode transducer later on. So the in ortho mode
Okay, sir.
transducer we actually use this, and Parvi sir also told me to work with you in, and he has a new concept, a new kind of waveguide structure. So in that also
Okay,
we
sir.
will need to do this structure, but that is later on. Okay, okay, but the concept should be there. So our B dimension should also be brought down in a similar fashion, and our B dimension was again our B dimension was, what was our B dimension? Our B dimension was 10.16, and if 10.16, sorry, 10.16 by 1.45, that is 7.02. So we can do that. 7.00 to 10.16, and linear count, it is with a linear count, so it will be symmetrical. 3. Okay, now what we shall do, we shall make it sync, so that our table shows that these are the combinations. Okay, yeah,
Okay,
and the
sir.
combinations are like this. Okay, we can do that. Okay. Now let us try, and we shall see beautiful things. Now let us analyze this. So whatever I am trying to connect with you, the ideas that I am showing, and through simulation, I am trying to verifying what I am telling you. Just not by just saying to you, I am just trying to link it to the actual what is happening. You can also see the
Yes, sir.
field, and you can see the fields to be like I have already earlier shown you, at higher frequencies your A dimension field will be much elongated, and there is a chance that two
Yes, sir.
modes will be there, and those things will happen in here also. All everything is same. After we do this, we shall convert it to our actual SIW structure and show you that even then we can maintain everything. That's the idea. So,
Okay, sir.
my advice would be to okay. I am also recording this, I guess. Yeah, and I shall also try to put it in the YouTube in your share with you. And yeah, it is run. Okay, you can see that my by when we are changing the impedance B by A ratio, different B and A combinations, our cutoff frequency is changing. And see, because we have maintained our 1.45 ratio, and we have brought our cutoff frequency to the same 6.557
Yes.
gigahertz. Okay, now this
Yes, sir.
dimension again can be utilized for your, and now So basically, if you can see what we have done, so you can animate, and our structures will actually show. See, so we have actually practically
Hmm.
brought the waveguide down to such a small size now,
Yes, sir. Hmm.
height wise, weight wise, and this is the dimension. So same W band waveguide, but we can same W band waveguide, but we can now. What is this? We can see the dimension change.
Hmm.
Okay, and everything will be the same.
Yes, sir.
Otherwise, everything will be
Hmm.
same. So that now, so basically, by introducing dielectric field waveguide, we have brought down the basic dimension. Now we shall do the another simulation on this. What is that? We shall first use this dimension so that now it is proper to use at X band so that the cutoff frequency is that 6.557 gigahertz or close to that, and my impedance is close
Hmm.
to that. And you can see my because we have maintained the B by ratio, the
Yes, sir.
impedance, even though the cutoff frequency is shifting, you can see. Let us see. So I shall apply the data and we can see what is happening. Can bring it down. Yeah, that's the problem. Okay, so this is the one, and this was the earlier one. So your cutoff frequency we are bringing down, but because we are maintaining the B by A ratio, we are able to maintain the impedance of the dielectric field waveguide. Okay, this is around the same range. Beautiful.
Yes, sir. Hmm.
Now we shall do another simulation. We shall start with the proper 8 to 12 gigahertz dimension for the 8 to 12 gigahertz waveguide, and next we shall bring down the B dimension such that now it will should look like a PCB. Okay, so
Hmm.
in a Teflon PCBs we can go for 1 mm 2 mm PCBs. So we let us do that at parametry, and we can reduce our B dimension only from 7 millimeter to say 2 millimeter. So 2 millimeter to 7 millimeter,
Seven. Hmm.
7 millimeter or 3 millimeter is also a good value. In there is a many a Teflon structure in 3 millimeter. Okay, yeah. So maybe steps of 2 millimeter. So 357. So let us go to one also.
Hmm.
357. So everything is there. Okay. So four numbers of B dimensions change will be there. So let us see what happens. So when you do that, so let us go and let us analyze our this thing. So if we only bring down the B dimension, what should happen?
Hmm. It will look like uh, a dimension square, I think.
No, if we bring down the B dimension,
B dimension. Okay.
uh,
B
so
dimension.
what will happen?
Uh,
Your impedance will go down.
Technically, yes. Okay.
Impedance will bring down. Impedance will get reduced.
Hmm.
So we should be able to see that. So let us see what is happening. Let us just rectangular plot is 1:1 and your B
Hmm.
dimension 1357.
Seven. Hmm.
This is report. So because we have not changed the A dimension,
Hmm.
our cutoff frequency remains the same, and we
Yes.
can still use this structure as 8 to 12 gigahertz X band waveguide.
Hmm.
Next, If we go for the Z parameter, sorry, port Z0, and then again if we change the same thing, we are bringing down the one dimension, what we have. You can directly see, even though our cutoff frequency remains the same, our high infinite impedance zone remains the same, we can directly see that
It is not really different.
our impedance value is just simply and very unitary method, right? Just by like unitary method, because it is a linearly related. The impedances are linearly limited. So if we bring down the p, our impedance just goes down.
So it's not really
How
different.
and see how the lowest value has how much value we are able to achieve. How what is the value we are able to achieve? Achieve or something, I don't know. See, from 241 ohm to 34 ohm.
34.
And you can directly see we are the 34 ohm for 1 mm and 241 ohm for 7 mm. So you can just multiply 34 by 7 and you will arrive at 241
Yes, sir.
or around or similar value. See what I'm trying to say is 34.55 34.55 into 7, 241.7. That is what I'm saying. The linear, there is linearly just changing. Okay.
Yes, sir.
So now let us do the simulation. Just drawing again. Go back to the waveguide structure, and let us do this animate box. Okay. You see the now you are able to see and appreciate
Yes, sir.
that it is simple like a PCB.
PCB.
And Teflon 3 mm Teflon PCB is very common. So let us use that 3 mm Teflon PCB, and we shall do that. 3 mm Teflon PCB will give you 103 ohm. Okay. And let us do that. Yeah. So, and this what I am showing is very important, because this concept, what is the actual impedance going in, that has to be known. And one more thing I shall show you, I have taken for these impedance calculations, I have taken in the excitation, I have taken everything VI. I have taken
Z.
everything ZVI. Why? Because when ultimately we are going to do this in microstrip to waveguide transition,
Yes, sir.
that time your microstrip will be in VI. So just to get an idea, idea, we are doing the same thing. Okay. Anyway, so this is
Yes.
your 3 mm. Okay, this is your 3 mm waveguide. So in 3 mm waveguide, our S parameter is, you have seen, this is our S parameter we are maintaining, and our port Z0 we are maintaining something like this, and we can utilize it from 8.4 gigahertz to this gigahertz. Okay, that's the idea.
Yes.
Now next we shall move to make it into SIW, proper SIW. We have made the
Yes, sir.
structure and we have seen the structure. Now let us copy this structure and let us paste over. And now the concept is whether, what I've been trying to say, that whether we shall be able to make a SIW out of it. Earlier it is a dielectric field waveguide. Now let us make it into an SIW. So what I shall do, I shall do very simple structure. I shall do, I shall make a cylinder or something like that. Yeah. Sorry. And it need not be cylinder. You can make it into a hexagon, or but your PTHs are normally cylindrical, so that's why people use this. I have been considering what will happen if we use this conical kind of shape, cone shape, because that is something that can be. uh, difficult, like different. Yeah. Anyway, so let us do that PTH, and we shall do some simple dimensions. What is the dimension? So you can even ask now Chat GPT or somebody. Even it is very well known. So SIW dimensions formulation. SIW PTH dimension. There is a simple relation. Oh, not it. Is so basically people actually why people use zero point 0.4 mm to 0.9 mm is normal PCB the fabrication actually is like that. So we can take zero point 0.4
Hmm.
mm, but this
Yes,
pitch
yes.
has to be maintained. Pitch is distance between two, and this pitch has to be
Hmm.
maintained. You can keep less, not more. So what we shall do, we shall put a pitch here, okay. And one more thing that we shall do, yeah, we shall copy, draw a long line or something like that, and draw, edit, duplicate a long line. Then start it from here. So like 0, 0, 0, enter. Then we can go for PY dimension. I do not know, something I should give. Um, yeah, 0.8 mm or something like that, 1 mm or something like that. 1 mm is okay. One is very close anyway. One, and I can keep the total numbers here. Say 20. Yeah.
Hmm.
One more thing I should do is so this is my duplicate along line vector. We'll change this as pitch, okay, and
Hmm.
make it. Let's make it 1 mm only now. And another thing is I should change the PTH. So that's the radius. So I should say the dia. Dia is 0.4 mm. That's as I told you earlier. And radius would be dia by 2. And your center position would be A, right? A by 2.
Two. Hmm.
Apply. And your height is the substrate height, that is B. Apply. And one more thing we shall do is that I want to do some simulations to see how the dimensions and everything affects my SIW. So what I shall do, instead of the old original block being whatever length it was, length, I shall define length as a function of pitch. So your length will be, because we are using 20 numbers, so 20 into your pitch.
Hmm.
And let us see whether it is working. Yeah, so because 20 numbers, so minus 1 it should be. So because the distance in 20 numbers, so 19 numbers of pitch is done. See, my PTs are done one side.
Hmm.
My PTs are done one side, and by changing my pitch, I can change the SIW structure. And what I shall do further, what I shall do is this dimension, this box one dimension, instead of A, let us keep it a little bit higher. I mean, let us keep it A1. A is still 15.76, but let us keep it at A1, and A1 be something like 20 mm, and this also be, because my substructure is actually maintained by the PTH position. So I don't keep to keep it this. I actually made the PTH positions at A and this at M. So now that is done. I should keep. I shall also unite all the cylinders for further easy control. United them, and then I shall also
Hmm.
make a mirror copy. Edit, duplicate, mirror. Okay, mirror. So tab 0, 0, 0. You can see I am putting zeros here. So this is my origin position 0, 0, 0.
Yes, sir. Hmm.
Okay, enter, and I am want the opposite side of x. So -1. Enter. My SIW is complete.
Yes,
But
sir.
it
Hmm.
says you have not put any metal on top side and bottom side, and I will say because this structure provides the HFS itself provides PEC, I have not given. But in this particular case, for ease of understanding, I am going to assign that. So I shall make the top plate. So what I have done, I am going to go to edit. I am going to go to selection mode, faces, top face. I have selected. I can directly assign it as a conductor boundary. Okay, and that is
Hmm.
one way of doing it. But I shall show you another way. I can what I can do is I can select the top layer, top face, edit. I can ask the this to be a create object from face. That way a sheet is created for the object from face. Then again edit surface. I can thicken this sheet to our 0.017 mm, which is a copper thickness normally. And I shall also ensure that thickness has been created. You can see the thickness is created. Okay.
Yes, sir. Hmm.
Okay, the thickness is created. And then I shall assign this thickness as copper. This is another, there are many ways to do the same thing. Okay, I am just showing you one way.
Yes, sir.
You could have easily just assigned this face as a boundary and that would have sufficed. But I just show you. So for the bottom, I shall do that. For the bottom, I'm just assigning boundary and yeah, uh, finite conductivity and use material, and I'm making it copper, or I could have done PEC also. And okay, so I have shown you
Yes, sir.
two ways, and I have done it in two ways. So and for the bottom, I have created a copper structure for the top, and for the bottom, I have created a boundary structure. Okay,
Hmm.
so these
Yes, sir.
finite conductivities are last day I had created. I am going to delete them because there is no need for that. Yeah. Okay, I'm just this is just to show you that this one thing can be done in many ways. That's it. Now
Yes, sir.
now let us do these cylinders. They had to be defined copper or something like that. Properties
Hmm.
copper apply. Okay, and next we shall check a validity of the structure. Validity is not there. Why? Let us see that in the message manager. Parts 120 and box 1 are intersecting each other. Okay, because you can see in HFSS what happens if one structure or one 3D model completely encapsulates the other, it does not show any problem. With whenever there is this intersection kind of thing, because the cavity is coming out
Hmm.
of a little bit, there is this problem. What we shall do, we shall
Yes,
subtract.
sir.
So from cylinder, from box one, which is the substrate in this our case. Now I can name it as substrate also. From box one, we shall select these two also, controlled by heading control. Then I go to draw, yeah. Then I go to subtract, and I can clone these objects. These two will be clone two objects before operation from the subs. Now if we again go to simulation and validate, okay, new problems have come up. Why? That is to see. Okay, validate. Okay, excitation problem has come. So what is the excitation problem? We have
Hmm.
not put any excitation. So let us put
Assign
that.
port, yes, sir. Hmm.
Wait for this area. So let us put an excitation. Uh, Assign excitation. Wave port. New line, and I shall do ZVI. I try to put ZVI always. Try to be consistent. Yeah. The both endpoints port must lie on the port. What is wrong? Invalid. New line. Okay. Okay. Still invalid. Why is it invalid? New line. Okay. Valid. So I was going to the top of the meter. So not the other way. Go to this phase. Assign excitation. Port. We shall also see the results, how the results change in different other tools. We need to go to the bottom one. Next, finish. You must always see that there are so many other things in the port definition window. Do not read or normalize or something like that. You can go to
Yes,
HFSS
sir. Hmm.
documentation and you find about what are those other things. Okay, I shall
Yes, sir.
create a color, give some color to it. Okay. Now we have put the excitation and we know everything. We know it should work from 8 to 12 gigahertz and everything. And now let us see. First validate. Uh, Now let us go for analysis and setup. Our setup is already there. Earlier setup,
Hmm.
last day setup. And because our design is still 8 to 12 gigahertz, we can stay from 3 gigahertz, but it doesn't matter because it will be much higher. So yeah, let us keep that. Let us keep that. Let's see what is happening. And now we run this thing. Go to setup and analyze all.
Analyze. Hmm.
Oh, I had not stopped the optimetrics. I should have stopped the optimetrics. Anyway, should not change anything. What we are trying to see, so we started from normal waveguide. We made it into a dielectric waveguide. Now we made it
Hmm.
that into a SIW and we are seeing whether results are same. Effectively,
Yes,
the
sir.
result should be
Hmm.
similar at least. Only thing,
Hmm.
because of the PTHs have a round structure, so it is going a little bit inside also, right?
Hmm.
From
Yes,
earlier
sir.
also, there has to be some changes in the position of the PTHs. Our A dimension will change as such. So there is that is why there is a term called A effective in SIW. Okay, there is a term called A
Yes, sir.
effective in
Hmm.
SIW. And I shall show you what have I given to you. Did you contact Orvo?
No, sir.
Anyway, yeah. I wish I had done this
Okay.
thing with Orgo sometimes because I have not
Hmm.
done this with Orgo. And he was so much confused when he started the work. I have given in this, but he has not updated anything. Okay, what to do? And where is your one? Manish. You see this
Also, result of. Hmm.
I try to maintain this your this slide. Okay, this is going to be your life changing. Everything needs to be there.
Okay,
Whatever
sir.
you are
Hmm.
simulating, you can just keep it there. Don't need to like if you are thinking you are creating some garbage, you can put that garbage on a single slide and write something on it and with a date. That way you will be able to mark your progress.
ওকে স্যার, রেজাল্টটা আসছিল না, মানে ঠিক ওই জন্য স্যার, মানে
Result
ওটা।
আসছিল না, but
হুম।
still you can do that and later on you will understand that this was my mistake.
ইয়েস স্যার।
You will forget. We
ওকে।
will simply forget. We simply forget. We do so many structures and we just simply forget. So our objective is right now to make this structure, right?
ইয়েস স্যার, ইয়েস স্যার। হুম।
And I will not make it this structure. You will do it yourself. I'm just showing you what we are doing. Okay, that is one thing. And I think I have another SIW list something in which I have given the PTH and documentation and something like that. Substrate integration. So I am what I'm trying right now is I'm putting a lot of effort to connect different similar concepts together and doing similar. Yeah, so this is the I have earlier shared this paper, right? This Kurdura paper is also I have
ইয়েস স্যার।
also given you.
হুম।
In that paper, you will come to this valuation, this A, S, P, and D, and how they are related.
হুম।
Okay. Although they have given the D or diameters as lambda g by 5, I keep it very small. The smaller, the better. And we can actually, the way we have created here, we can see. Okay. I hope the results are there. Yeah. Yeah. Yes. You got it. See,
ইয়েস
see
স্যার।
the beauty.
হুম।
Can you see how beautiful SIW structure we made?
ইয়েস স্যার।
Because our time is earlier, the cutoff frequency was 6.557 gigahertz, but
হুম।
because I have put the PTHS in the at the center. I have centered the PTHS on the earlier SIW earlier A dimension boundary. What has
হুম।
happened? The actual metal wall has shifted a little bit inside the waveguide,
ইয়েস
and
স্যার। হুম।
thus my effective A dimension has gone lower, and that is reflected here. So my cutoff frequency has gone from 6.577 gigahertz upwards to 6.69 gigahertz. So that is the thing. So now we just have to adjust my A dimension to adjust my A effective dimension with the position of the PTHS. This this waveguide A dimension wise position, the x direction wise position, and by changing that we can again create it into that same structure. Here you can see we have been able to achieve 40 dB in the return loss. There is a perfect waveguide, and our impedance is also similar as the earlier one. So this was our impedance, right? 103 ohm or something
ইয়েস
like
স্যার।
this.
হুম।
135 ohm, 8 gigahertz. So yeah, 8.2, 129 ohm to 103 ohm, and you can see here
হুম।
also in this structure also 130 ohm. So what I'm trying to point out to you here is that if we do everything in dielectric field waveguide, we can just simply by maintaining our PTHS, we can just simply make it into our SIW.
ইয়েস স্যার।
And this
হুম।
is true for everything, for antenna, for your whatever structure, yeah, your filter structure, everything.
ওকে স্যার। হুম।
Okay, so this is the idea that I was trying to do, and we have been now one more. Let us do some parametric concept. What will happen if we change the pitch? So when we change the pitch, what is happening? We are changing the. Okay, one more thing. One thing I have not done here, and that should be done. So my this phase is automatically taken as a PEC. So that should not happen. So you might question that
হুম।
that is again a PAC. How do I know the energy is contained inside? Yeah, of course. Once we can show the field. I believe the field will be able to. showcase the actual structure. So let us do that. Fields, or field should be contained inside my uh, this thing, and it is contained inside my PTHs. See how beautifully
Yes,
is
sir.
it contained. Okay. Now, but still, you will say that somebody might say it is not actually following. So what we shall do? We shall select this outside outskirts, this one and this one, and assign boundary and put it into a radiation boundary. And then we shall run the structure again while adding a parametric for the pitch. So
Hmm.
pitch is 1 mm right now, and we
Yes,
shall
sir.
bring the pitch to say 3 mm. I don't know, and say
Hmm.
1 mm step. So and this is stipulated what will first animate it. So to see my structures are valid. Okay, okay,
Yes, sir.
and I shall do one more thing because I want to the results to be good. So subject. So what I will do is I shall also add another value. Add 1.5 mm just to see. That way it is more simple.
Hmm.
See, Moni, why I am spending this much time with you is to I want you to understand the fundamentals well. Once
Yes,
you
sir.
understand this
Hmm.
fundamentals, you can think on your own. And the major idea in research is to be able to think on your own.
Yes, sir. Hmm.
So we did the parametric, and we shall. What should we expect is when we are increasing the distances between the PTHs, the energy should
Hmm.
start leaking out,
Yes, sir. Hmm.
and we should be able to see that. That's the next. We shall what one more thing we shall do. We shall put an outward full boundary, outward waveguide, and boundary encasing the full waveguide, and there we shall be able to see what is happening. And maybe also we can use lamp code or something like that.
Hmm.
Okay, I think it is done. No, it's still. If you put your high hole diameters and your pitch
Yes.
length,
Yes. Hmm.
if you select them correctly, then there will be a seamless transformation. That's what it's.
Hmm.
Now we have done some simulations finished, and because of the PTHs, now the designs are taking much more time to run. Okay,
Hmm.
now let us see what is happening at 1 mm. So 1 mm result is this one only. At 1.5 mm. So I have changed the gap. What should we expect? Our return loss should go a little bit. First, we should do this. We should fix our these values so that we are able to see what is happening. So I'm going to fix the scale. Okay, I'm going to fix
Yes.
the scale so that we can compare. Okay, so the earlier one is less than minus 40 dB with 1 mm pitch. So we are going to 1.5 mm pitch. What is happening? Yeah, it is going to 30 dB.
Hmm.
And
Yes,
let us
sir.
go to 2 mm pitch. It is going upwards.
Hmm.
Okay, it's going now. It is 30 dB, touching 30 dB. So at 1 mm it was below 40 dB. Yeah, and at 2 mm it
Hmm.
is touching 30 dB. And now let us look at also the fields of what is happening in the fields. What is happening in respect to fields? I don't know. Fields are not being plotted. I don't know. I think the running is run. There's still something to run. So, okay, the impedance wise, what is happening? Okay, one more thing. My all these results are updating along with my change in the parameter, because all these results this in the modify report, you can see in the families we are putting nominal. So because of the
Hmm.
nominal value, if whatever whenever we are choosing one value, that becomes the nominal, and that's why it is updating. If it is fixed to some other value, it will not update. Kindly check that what you are doing. Okay, whenever you are doing that.
Okay, sir. Hmm.
মানে তোমার যে মানে তোমার যে see that with increase in pitch,
Hmm.
there is this field leaking out effect
Field
is there.
leakage. Hmm.
Field leakage is there. So yeah. So again, view analysis result, just to show you, we can again look at the field once more. Yeah. So at one, when our pitch is very small, though there is no gap in between, and our energy is completely contained inside. But as we go along
Hmm.
increasing the pitch, our field will come out. Let's do that. OPT will be there. Oh, did not work. Yeah, maybe 3 I shall to be there. Yeah, our field is coming.
Yes, sir.
Okay, so
Hmm.
I believe for today let us stop here. Okay, I shall
Hmm.
suggest
Okay, sir.
you to utilize this structure and whatever we learn from today to go to
Hmm.
this paper, again Kurdure paper, and our major idea is to first emulate this structure. Okay,
Okay, sir.
and
Hmm.
if you can devote the day to day, and by night or something you can do something like this, I can again help you in night to achieve this structure. Okay,
Okay, sir.
okay, so let us stop here for now. Bye.